Okay, so I want us to look at the question I gave to the class, okay, in our last meeting. And the question is that a body at rest is given an initial uniform acceleration of 8.0 meter per second squared. So the initial acceleration of the body is 8.0 meter per second squared. For 30 seconds. So this is for a period of 30 seconds. After which the acceleration is reduced to 5.0 meter per second squared for another 20. So acceleration is reduced to 5.0 meter per second squared for 20 seconds. The body maintains the speed for 60 seconds. So the third part of the motion is that the velocity is maintained for 60 seconds. Okay. Constant velocity for 60 seconds. That's the third part of the motion. After which it is brought to rest in 20 seconds. So then body brought to rest. Brought to rest in 20 seconds. So it's like there is this uniform deceleration there. Okay. So body initially starts from rest implies that here the initial velocity is 0. So when we look at the first part of the motion, if the body starts from rest and its initial velocity is 0 and it is uniformly accelerated, and this is the rate of acceleration within this time, then it means that the final velocity V of the body is equal to U plus AT, which is 0 plus 8 times 30, giving us a velocity of 240 meter per second. So this is the final velocity. Then in the second part of the motion, the body's acceleration is reduced. Please, a reduction in the body's acceleration isn't a deceleration. Okay, it is like an acceleration of 8.0 meter per second squared simply means that the body is moving at a velocity of 8 meter per second within every second. Okay, where its velocity is constant or it's uniform within equal time interval. So what this means is that the body is moving at a velocity of 8 meter per second within every second. Then the body's acceleration was reduced. It's reduced. So instead of moving a velocity of 8 meter per second within every second, it is reduced to 5 meter per second within every second. it is not a deceleration. A deceleration has to do with decreasing velocity in the opposite direction. So for a deceleration, we expect that the direction of the body must change. But over here, I'm in one direction, but I'm reducing the speed within every second. That's what it means. So if the body's acceleration is reduced to 5, then what will be, this is the initial velocity because it's a continuous motion. This came in after attaining a final velocity of this, and the body or whoever, if it's a car, the driver felt, oh, let me reduce speed. Okay. Okay. So the initial velocity for the second part of the motion will be this. So let's use that to calculate for the final velocity. So V2, 2 to denote the second part of the motion will be equal to U2 plus AT. U2 becomes the final velocity of the first part. So U2 is equal to 240. Therefore, V2 is equal to 240 plus 5 times within a time interval of 20. So we have 240 plus 100, giving us 340. So it implies that if he had not reduced the acceleration, okay, to this, then the final velocity would have been greater than what we have in this case. So this is happening because he had reduced acceleration. All right. Then the third part of the motion, he said he maintains this velocity for 60 seconds. And then the body is brought to rest. Okay. So this will be maintained for 60 seconds. Then from there, the body is brought to rest. So that bringing the body to rest would also, go through a uniform deceleration. So we can decide to calculate for the uniform deceleration. So look at it, brought to rest, meaning coming to a stop. So V, using the same equation, V is equal to U plus AT. The body is coming to rest in the final part of the motion. So the final velocity is 0. It's equal to the initial velocity, which is 340 plus A is what we are looking for, times 20. So we have 20A equal to minus 340. Therefore, A will be equal to minus 340 divided by 20. And this is 17 minus 17 meter per second squared. So this is the uniform deceleration of the body. Okay. Now let's look at what we are asked to do. Using the graph, calculate the speed, maximum speed attained during the motion. So let's plot, we need to plot a velocity time graph or speed time graph for this motion because we are to use the graph. Okay, so let me adjust the screen so we can capture. So we are starting from rest, then attain a velocity of 240, then 340. So this is velocity time graph. So 0, 240, then 340. Time, we are starting with a time of 30 seconds. So 30, then 20, giving us 50, plus 60, 110. Then finally, 30, 20 seconds. So 130 seconds. So the body starts from rest. So within 30 seconds, there was a uniform acceleration. And the final velocity is this. So this 30 seconds must connect this velocity. So that's the first part of the motion. Then the velocity is reduced to 5 meters per second square for this second. So this has to do with reduction, a drop in the gradient. A drop in the gradient or slope of the second part of the motion. Or let me extend the time so that it will drop the gradient well for me. So I'm assuming the 50 seconds is here. And then the velocity of 340 is here. And I'm making these changes so that I'll have a lesser gradient compared to the first one. Good. Because the gradient is reduced, the acceleration is reduced, we need to have a lesser gradient compared to acceleration of 8. So that's it. So if the acceleration is reduced, then the slope of it must be less than the higher acceleration. Yes, this must have a greater slope than this one because the acceleration of this is greater than that. That's all. Then from there, the body moved with a constant velocity for 60 seconds. Constant velocity. Then the body is brought to rest. Uniform deceleration. So this is the motion. This is the motion. Okay. Now let's go back to the question. So using the graph, calculate the maximum speed attained during the motion. Obviously, maximum speed, the maximum speed attained is 340 meters per second. Then II, average retardation as the body is being brought to rest. Okay, so we know we've calculated, but the average retardation or deceleration is equal to the slope of this uniform decelerated motion. So change in the vertical, 340 minus 0 over a time of 20. And this is minus, sorry, 0 rather. 0, final minus initial. 0 minus 340, which is minus 17 meters per second squared. Total distance traveled during the first 50 seconds. Total distance traveled during the first 50 seconds is the area of this. Okay. And that will be half base 30 times height 240 plus, this is a trapezium, half A. A is 240 plus B is 340 times height. The height is 20. So we have 10. So in all we have 15 times 240 plus, this is 580 times 10. Okay. And 15 times 240, this is 3,600 plus 5,800. So this plus 5,800. We have 9,400 meters as the total distance. Okay. Then the last question, average speed during the same interval as III. So the average speed during the same interval as III is the total distance V bar or V average. Total distance 9,400 divided by 50. So we have 940, 940 divided by 5. And this is equal to 188 meters per second. So this is the solution for the whole problem. Thanks for your time. If you have further clarification to be given, please contact me through my personal WhatsApp line. In fact, until then, bye-bye and enjoy your Easter festivity. Bye-bye.